Okay. So on Wednesday, we started the pipelining topic, and then we stopped at this. And then in the last couple of minutes, I gave you an idea about what is going to happen. For example, if there is a data dependency, and then what might be a possible solution. Well, first of all, what is a data dependency? Look into these two instructions right now. If the load would require register 3 to 5 for the address, how does the load execute? Well, we know from the ISA lecture that I need to take register 3, add it to A, get the address, go to the memory, bring the data and put it in register 4, right? The problem is this resolving of the address of the load happens at the execution stage, correct? Because I need to add two things, so I need to use the AD. And then once I do this in the execution stage, I'm going to take the address, access the memory at the end stage. And the problem we face is at the execution stage, R3 is not ready. Why? Because it's going to be written by the add instruction, the previous one, and only updated after the write back stage. But how does the add execute? Well, take these two, add them in the execution, do nothing in the memory stage, go to the register file in the write back, and write the result into R3, right? So the new result R3, which in our example was 3, and I assume it was originally 5, is going to happen only after cycle 5. But the load needs it at cycle 4. Previously, in a single cycle or a multi-cycle but sequential processor, this issue wasn't there because the load wouldn't even start up until cycle 5, right? So by the time it needs it, just cycle 8 in that case, the result is already ready. This problem only arises because of the pipeline, because you execute things in parallel, right? You create some dependency. And we said in reality, this is what we call the data dependency, right? And it creates what we call a read after write hazard, as we'll discuss later today. But then we also discussed very quickly what might be a possible solution, right? We said fundamentally, the value that I'm looking for, which is 3, well, it has already been computed. It's not written yet to register 3, but I don't care about register 3 if I can get that result, right? So the result is already on fly right now. On fly means it's not written yet to the register file, but the add, in fact, has it ready at the end of cycle 3. Because this add operation happens at the execution stage. So by the end of the execution stage, the ALU output has the value 3. So if I can take it from the ALU output, I've solved the problem, right? You see, so it's an artificial problem because of the thinking that I need to wait for the data to be written to the register file. But in reality, I don't need to do so. And we call this solution bypassing or forwarding, as we will see later today. Okay? We went through this slide already. So one question we discussed last time, and it's very good to revisit, is why is pipeline, because it's very related to the topic of hazards that we're discussing today. Why is the pipeline clock period is larger than the delay through data path divided by the number of pipeline stages? If you think carefully, we started last lecture by saying, okay, in a single cycle processor, my clock period is too large. Well, in our example, it was 50 nanoseconds. And then I said, I'm going to throw in 5 registers to have 5 stages, right, or 4 registers to have 5 stages. And those 5 stages, theoretically, should allow me to improve the frequency by 5x factor, right? Because you simply divide by 5. The amount of work that I need to do in 50 nanoseconds, if I divide it by 5, well, it will be 10 nanoseconds each. But then we said, in fact, it's not 10 nanoseconds, it's not even 11. We said it might be 12 as a reasonable estimate, right? So why that's the case? What might be the reasons for that? We mentioned a few reasons last time, but good to revisit. The question again is why you think the pipeline wouldn't have the ideal improvement that if you throw in 5 stages, you improve your clock speed by a factor of 5x. Because in paper and pen, this is what should happen. There's an amount of work that you need to do in 15 nanoseconds. You bring in 5 people, then they should finish in 10 nanoseconds. Thank you. So one reason is that we said, because you throw in registers, latches, you need to accommodate for the writing and reading from these registers or latches, set up whole time operation, and then this adds some extra delay. This is definitely one reason. But this reason also existed in the multi-cycle. So if we can attribute The one additional nanosecond we added for the 10, so it became 11 in the multi-cycle. This might be the reason. But then we added another one for the case of the pipeline. Yeah, so the things that we talked about at the beginning, that there are some dependencies. Those dependencies don't give you the ideal behavior of the pipeline. You need to push things away, right? In this case, we managed to simply solve the problem of delaying the load and saying take the result directly from the bypassing solve with the problem. But bypassing does not solve the problem all the time. And also to figure out the bypassing logic to add extra delays, right? So that's another reason. What else? Yeah, exactly. Thank you. That's the third reason. So now we combine three reasons why, in fact, we need to add extra delay. The first reason that we mentioned is due to the latches or the registers. The second one is due to the hazards. And the third one due to the fact that if you look into a pipeline, something like this, we are under the assumption that every single stage of this is taking a single cycle now, or generally they're taking equal time, because we dedicate the frequency based on how much work you need to do in each one. But it's completely realistic to say the memory might take more time than the execution, or the execution might take more time than the recode, right? So those stages don't necessarily take the same amount of time. When I determine my frequency or my clock period, I do this based on what? If they are taking variable time, what should I accommodate for? The longest one, right? And this adds to the delay, right? So the third reason is that basically stages don't take the same amount of time and you have to accommodate for the worst. Good. These are the three reasons we have here. Latches add delay, pipeline stages have different delays, so the clock period has to accommodate for the maximum, and simply there's some extra data path that you need to handle due to dependency, whether it's the bypassing logic or the stalling logic, or even the need to force an instruction to be delayed a little. All these reasons lead to the fact that, well, if pipelining are good, pipelines are good, why we don't have simply very long pipelines, right? If you look into your current processors, you don't, for example, have a processor that has 100-stage pipeline, because the more you go deeper, we call this deep pipelining, the more you increase the stages, the dependencies will increase, you add more registers, so the delays will increase, so the overhead start taking over the benefits you get. You get diminishing returns, right? And this what stopped people from simply experimenting with deeper pipelines, and they stop at a reasonable number. This reasonable number will varies. If you're talking about an ARM processor in your mobile phone versus an Intel processor in a server or in a laptop or desktop, well, they vary heavily. Like Intel, you talk about 15 to 20 stages. In ARM, you usually talk about less number of stages, less than 10, because they consume less power, they are more embedded. But there is a limit, basically. Good. So the second thing that we also discussed, why is pipelining CPIs larger than 1? We said ideally, if you observe, if I stop here, if I'm an observer and stopping here, while looking into the output, ideally I should be expecting one instruction finishing every cycle, correct? So my IBC instruction per cycle is 1, which means in return, my CPI, the average cycles per instruction, is also 1. And I'm talking here about the effective CPI. Every instruction takes more, 5 or more, but effectively I'm getting 1 instruction per cycle, as if I'm executing every instruction in a single cycle, because they overlap, right? We call this effective CPI. But that's the ideal scenario. Why ideally the CPI is large? Well, why practically the CPI in pipelining is larger than 1? Well, for exact same reasons we just discussed, right? Like if you look into that example we have here, there is a dependency. If I didn't have the bypassing solution, I need to push the load instruction a little bit, so I will not be receiving 1 instruction every cycle, right? So the ideal, the best you can hope for, we call this what is the correct term? The envelope of the performance, right? That's the maximum. That's the best gain you can obtain, right? You put this in front of your eyes because you know that you'll never exceed that, but you usually have less than that. Right? Why I have less than that? Again, because of all the dependencies we're going to discuss. Bypassing logic leading to stall, pushing in instructions a little bit. Good. So if I want to calculate the pipeline CPI, I would have to take into account then the stalling cycle. So ideally it's 1, but I'm adding some extra delays due to the stall penalties. How do I obtain the stall penalties? Well, these stalls happens for certain scenarios, some dependencies. So I need to know what is the frequency of the stall, and if I'm stalling, how many cycles do I take, right? One thing also that will lead to the topic of out-of-order pipelining is that in order processors, the stalls in fact add. They don't hide each other. They don't really overlap. The reason for this is, and we will have numerical examples later on, but let me show you a very simple scenario in our example here. If I was to delay the load, to basically start from here, maybe I should draw a cleaner picture. If I don't have bypassing, so I'm going to redraw the add to be fetch, decode, execute, memory, write back. And this is one. Oh, but now I pushed everything. Okay, that's good. So let's start from here. Fetch, decode, execute, memory, write back. And this is our add instruction. Then in the load, if it had that dependency and I don't have bypassing, so I fetch, decode. In my decode, I do resolve the dependency, because in the decode stage is where I know what are my source operands, because this is when I understand my instruction, right? So in that case, when I decode my sources, I know that one of my sources dependent on the previous instruction. Then I have to wait. So I stall. How much do I stall? Well, I stall until I know that I'm able to obtain my address. So I add a stall stage here. We call this S. So there is a stall here, which means, well, you are not executing anything, right? I should add this stall in a different color, but anyway, so stall, and then you execute the load, you do the memory, and then you do the write back. When we come to the store instruction, you start fetching it here. If the previous instruction is stalling in an in-order pipeline, we said we enforce the order, right? So what is going to happen is you have to stall this one as well. And then you continue, right? You fetch, decode, execute, memory, write back. Which means in a normal in-order processor, if one instruction stalls, all the subsequent ones will stall. But also that means that the stall times will add up, because if you think about the store instruction, if it has a dependency, for example, if I was to turn this one to be register 4, now I created another dependency between the load and the store, correct? Which means when I try to recode here, I also need to stall until I obtain the data, right? So there is another stall that is going to happen later on, correct? And the stalls will add up. Make sense? So simply, this is the meaning of why penalties add up in a general in-order pipeline. And that's one reason why people mostly have out-of-order processors, except for embedded domains. And then, so to calculate the effective CPI, I would say, okay, ideally I have one, but I have some extra delays. Based on this type of the delay, for each type of stall, I would know how much time I need to wait. For example, if there is a stall for a load that is waiting on the execution stage of the load to finish or the write back stage, that means, for example, it might be 2 cycles, similar to our example we have. So you add this delay here. And then how much this happens? How do I determine the stall frequency? So the stall cycle is okay, it's an artifact of the pipeline. We know that I need the result from that instruction, I need to wait. But how do I determine the stall frequency? What does it mean to me, stall frequency? I mean, to calculate an effective CPI, you add your delays, but here, this is basically an effective delay. So everyone takes some time, and then this is the rate that this is happening at, right? Recall in our performance lecture, to calculate the effective CPI of all the instruction types, what we have done is have the instruction frequency, the rate, what you have done in lab 1, right? Like, for example, the memory happens 30% of the time. So that means, like in the application, that means the memory frequency, the memory rate in your application is 30%. So you multiply 0.3 by the time that it takes the instruction, like the memory instruction to execute. The same thing here. You look into the stall as if it's another work that you need to do. How much time it happens, how many times it happens, and how much time it takes when it happens at once, right? So for example, if the stall frequency is having 30% between instructions, I multiply 0.3 by how much extra time I need to suffer. This we say is an artifact of the pipeline, right? But how do I calculate the stall frequency? It's based on what? It's based on the application itself, right? Similar to any instruction type, because they happen because of dependencies. If you create a program that has a lot of dependencies, then this program is not amenable to pipelining, right? It's in fact not very suitable to pipeline. And by the way, that's one of the main reasons why people deal with, as we will see in another lecture, into multi-core and multi-threading, because the amount of parallelism into modern applications is very, very limited. It's very natural that when you write an application, there will be a lot of read-write dependencies. I don't really throw in writes to registers that I don't use later on, right? So most of the time, in your control flow, you write programs that naturally will write some data and then use it later on. So there are a lot of dependencies within applications that limits the amount of parallelism within an application. Pipelining is a concept that is called instruction level parallelism. So pipelining leverages the fact that some instructions within the program are independent. If they start becoming dependent, the benefits I'm getting from pipelining is in fact diminishing, right? Because I will create a lot of dependencies. I have to stall all the things that we're talking about right now, start materializes more and more, right? So people deal with, okay, if you have limited ILP, instruction level parallelism within an application, then, well, what about across applications? If you have two different programs in your laptop, they are completely independent, right? You don't assume that any instruction in that application will depend on another instruction in an independent application. And hence, you can execute these two applications truly in parallel, right? So the amount of parallelism in two different applications is way higher than within the same application, and hence having multi-threading, multi-core is in fact a winning kind of architecture concept, right? That's why we have it nowadays, very apparent. Good? But that's basically the insight behind pipelining is only leveraging parallelism within the same application, instructions of the same application. Good? You try to extract as much parallelism as you can, right? But you will hit a limit at the end of the day. Good? And a very important thing is you have to make sure, this is also we discussed last time, you cannot really trade correctness for performance, right? For example, if I go here and say, okay, you know what? I'm going to, I keep going back to this example, but I just want to give you something very simple before we get into very numerical intelligence ones. So if I cannot really say, if this load has a dependency in R3, I say, okay, forget about the new value of R3, just use the old one and continue. This is making sense. It's incorrect. I mean, I'm not looking for finishing earlier for the sake of finishing earlier if I don't have the correct result, right? So you must obey the correctness of the program, otherwise the hardware is doing something wrong, right? Okay, good. And basically, well, already did also discuss this, is that those dependencies will create hazards, and then you either need to store or do some sort of bypassing forwarding, some techniques that you can handle, right? And this is all that we need to discuss today: data dependencies, pipelining, hazards, and bypassing. So we need first to differentiate between two different things: a dependency and a hazard. You need to differentiate between something that is natural in a program and the impact that it might lead in performance. So we call the dependency, it's the relationship between two instructions. There might be data dependency, there might be control dependency, and there might be even structured dependency, as we'll see later on. Those dependencies, as I was saying right now, they are very natural in programs. If you don't have programs that have a lot of instruction dependency, they are not in fact practical programs. They are two examples, right? So dependencies are very common in applications, and you cannot avoid them, and something that naturally happens, right? But the hazard that the dependency might create is the thing that is bad for the performance and you need to handle, right? So there is something that happens naturally from the software perspective, but it has a bad impact on hardware, and you need to solve that problem. You cannot avoid dependencies, but you can avoid as much as you can their bad impact in performance, right? So we target to solve hazards. We cannot solve dependencies, because dependencies are natural in the program. I don't modify the program. Hardware assumes software is given as is. You don't touch the software, right? Good. So data hazards, we already had an example of this. We look, well, these are the three instructions that were in fact independent. So I will pass some of these things. Yeah, so here. So assume that we have two instructions, add and add. Well, I'm adding R1, right? Well, R1 and R2, add them, put them in R3, and then add R4, R5, and then write them in R6. These instructions are completely independent, right? So that means they are 100% pipelinable, right? Or parallelizable, right? Which means we execute in the pipeline without any dependency. Very natural, ideal scenario, don't care about any hazard handling there. But if you start adding dependencies, either in the load example I have given earlier or here, where the result of the first add is going to be read by the second one, now you created the dependency, right? We call this a read after write dependency, because the first one writes, the second one reads. And then, well, if you have that program here, well, dependencies can, well, what this snippet is saying is that dependencies can in fact manifest in multiple subsequent instructions, right? For example, the add is writing this one, then the load is reading it. Well, add I is also reading that one, and then the store is also reading that one. That means all these three instructions are dependent on the add operations, right? By the way, between these three instructions, is there any instruction that is writing R3? Add is writing R3, but what about the load and add I and store? Yeah. Are we writing R3? Yeah, I'm asking this question for that purpose, because this is one of the very common mistakes. I don't know why this is happening, but it's very common. Store here is not writing R3. Store writes only to the memory, right? Yeah. So a store instruction solves an address, take a value from a register, and put it in the memory. So the store, if you remember the ISA lecture, does not write to the register file, right? It writes only to the memory. So all these three instructions are reading R3. So they're consumers, right? While the add is the one that is writing into it. The actual dependency is between each one of these and the add. If there is a read after read, seems like a dependency, but in fact, it's not an actual fundamental dependency, right? Because no one is impacting the other. If I execute this one before this one or this one after this one, it wouldn't impact anything, right? So reads after reads are not dependencies. It's read after write that creates the dependency. Questions? Good. So well, how to execute correctly in that case? Well, I start executing my add that writes into this. The load comes into this, the execution stage, needs R3. So if I just execute naturally, well, the program is in fact broken because I'm reading the old value. But in reality, as we said earlier, I can take the value of R3 from the output of the ALU without waiting for the write back. Here comes the circuit that does the bypassing, the thing that you read from the ALU before waiting for the write back to happen. If I add that wire here and this mux, what's going to happen? I'm saying the input to the ALU, for example, here R3, that is going to be read by the load, can come naturally from the register file, that's the normal path, but also might come from the previous result of the execution stage, right? And this is what solves that problem, that R3 is written by the add. The result is ready here. Don't wait until it's being written 2 cycles later. Just take it directly on the fly from the execution unit. Right? So adding that wire and this mux here is what executes the bypassing logic, right? And this is why it's called bypassing or forwarding. You don't wait for the result to be written in stable state here, but you take it from the wires directly to the input. Does this make sense? So now I have a mux that says my input to the ALU might come from the register file or might come from, well, the previous result of the ALU. Based on what do I select? How can I create the logic that feeds this multiplexer? As we have discussed in the control path, anything here would require some circuitry to create the control signal, right? So what is the logic behind selecting either this one or this one? For the example we just have here. The logic here is say, I do bypassing if one of my sources is the destination of the previous instruction, right? This is basically how can I write it. If the previous instruction destination, the 5 bits in the instruction, that if you remember the IC, we have 5 bits for the destination. If the 5 bits are equal to the 5 bits of one of my sources, I have a read after write dependency. You bypass it from the execution stage. That works only for this thing because you also need to say, okay, I want to make sure that this is an add, because for example, if this was a load, the result will not be ready here. The result will be ready after the memory, right? So to be able to bypass it from the ALU, you also want to make sure that your previous instruction is an arithmetic instruction. The arithmetic instructions are the ones that have the result ready after the execution stage, right? But it adds to the complexity for now. Let's say, okay, my source is the destination of the previous one, right? Make sense? So now, okay, so as we are saying right now, to start complicating things, sometimes, okay, let's go to the simple one and let's think a little bit. So in that case, I'm reading the output from the ALU. But in reality, what if the load comes, for example, 2 cycles later after the add itself? Like I have something like this, add, and this is 3, 2, and then 1. And then I have a subtract that is something completely different. And then I have the load. If I want to draw the pipeline of this example, how do I draw it? Well, maybe it's better to be clean. Okay. As you can tell, I hate Apple products. Keep. Okay. Okay. So I have these 3 instructions. So I had the add. I forgot the exact namings, but let's say it's an add R3, R2, R1. I have a sub that is completely independent, R5, R6. Then I have my dependent load instruction that is going to load into R7, something that dependent on the value of R3. It's very important to understand what's going to happen right now, okay? I want to draw the pipeline to understand when the dependency happens. So I fetch, decode, execute, memory, write back. First instruction, no dependency, so there is no issue. The second one is also completely independent, right? So it just goes very natural. At cycle 6. When it comes to the load, okay, I fetch here, I decode, I find out that I have a dependency, right? It's this R3 and this R3 here. So if I naturally stall, I would have to stall until I finish the write back of this one. So I stall for a single cycle and then do the execute and then the memory and then the write back, right? But if I don't want to stall, then, well, that's one possibility with no forwarding. But let's say we don't do this for now. Let's say I enable forwarding. But if I want to the execute right now, from where do I get the result in the execution unit? If I say, as we have said up until now, is that if I'm forwarding from the execution to the execution, you can imagine that's already wrong, right? Because the execution right now already have the result of the sub, right? So I cannot really forward from the execution register. From where do I forward? If you understood the flow that we have done for the pipeline through the data path, originally the add, this one, when it did finish the execution at cycle 3, the cycle after, it moves to the register that is between the memory stage and the write back stage, right? Correct? Because every cycle, you move the value from one register to a subsequent one, right? This must happen. So in that case, I need to forward from the register between the memory and the write back. So you forward from here to here. Does this make sense? So in some cases, your result might be ready at the end of the execution. You can take it from there, but in some other cases, you might need to take it from the memory stage. In some other cases, you might need to take it directly after the write back stage, right? Make sense? Good. But what does this entail? So it entails that, in fact, this simple figure here, this one here, only accommodates for the case I'm getting it from the execution stage. So I need to add another wire that takes from that register instead, right? This one does, okay, how to map that one to the pipeline figure that we have. This is execution, this is X stage, this is the register between the X and the M, and this is from the M to the write back, right? So we call this M, this is write back. So I need to add another wire here that takes also from the memory, right? This one, at the end of this one, which is simply by the end of that multiplexer, to also the input of the ALU to accommodate for the example I just gave you. Does this make sense? Questions? So now I forwarded after the ALU and after the memory stage. Okay? And then, as you might imagine, we have only thought about one input operand. But in fact, in case of the add dependency, I might also need to do the same thing for the second operand, right? So you repeat the exact same logic here and here. Which means, if there is no dependency at all, this path will go through the multiplexer. I'm reading from the register file. If there is a dependency and I can forward from the output of the ALU, then this path will execute. If there is a dependency and can forward from the end of the memory stage, then this path will work. And this is a possibility for this operand register or that operand register. Make sense? Okay. Good. Yeah, there is another thing here. Okay, so we're building one by one. So we are done with that one, which is simply I'm forwarding, I need my result at the beginning of the execution. But in reality, not all instructions need the value of the register at the beginning of the execution. Can you think of an example where an instruction might need the result somewhere else at the beginning of another stage? This might be a bonus one. It's an easy question, but it means you understand really what's going on. So what is the question again? So arithmetic operations need the operands at the beginning of the execution stage because you need to execute. But not all instructions are like that, right? Yeah.
You want to store it back to memory.
Exactly, thank you. So if I want to store, then I don't care about if I have a store instruction, I don't need my register value at the beginning of the execution. I need only for the store, I still need something at the beginning of the execution. What do I, so the store in fact uses two different inputs at two different times. It uses the address, right, register, to compute at the execution stage. But it uses the data register, the one that is going to write to the memory, only at the memory stage, right? So in that case, I need to add also another bypass logic here that is simply coming from the memory to the input of the memory. And here is the example. So assume, for example, I have a load instruction that is going to load a value into R3, but then there is a subsequent store that is using it. And then it's using it at the memory stage. So I need to forward from the memory to the memory. The load will bring this value after the memory, and the store will use it at the beginning of the memory. Good? Is it becoming too hard? Yeah. You can imagine if we have 20 stages, how much forwarding and store logic we might need, right? This is why, in fact, people stop and say, okay, this doesn't make any sense. We should limit it to certain logic because the overheads start becoming the dominant factor, right? Good. Okay. So all of these signals, as we were discussing earlier, need to be driven from the control unit, which is simply done at the decode stage. So I have some bypass logic here, and this bypass logic is the one that drives all these. Well, I'm only showing one, but it also drives that one and drives that one, right? And if I want to have the simple example that we had for this simple one, we said, okay, my source, one of my sources, let's say, for example, I'm writing the circuitry that drives that signal. So if my source, and this is source one because we're talking about that path, it would be source two if we're talking about that path. My source one is the same as the one that the memory is going to write at. That destination, then I select 0. 0 is that one, right? That's basically from the execution to the memory. Or if my source is coming from between the memory and the write back, which is this one, then I set my selection to 1 to select that path. Otherwise, the normal path, there is no dependency, then I just select 2, which is my normal path that's coming from the register file. Good. So this is basically a circuitry that you need to write if you were to implement a simple pipelining processor with bypassing to only handle this one, and then you need to handle all the possibilities. Right? And they will usually write a complex finite state machine to handle all of them. Okay, good. So we discussed already forwarding from the execution to the memory, execution to execution, from the memory to the execution, and from the memory to the memory. Okay, now there's one of the complex dependencies that, in fact, up until now, all this bypassing logic cannot handle. If you think about all these three examples, so it happened that I would have my result ready. Okay, so the main observation that the bypassing is using is that your result is in fact ready before you start needing it, right? It's not written to the register file, but it's there somewhere. And then it's your role to figure out where it is and bring it, right? But it does not solve the problem if the result is not computed yet. There's nothing you can do about it, right? One scenario where this cannot happen, like bypassing does not help you, is that if you have a load operation, and this load operation is bringing something from the memory, so it happens at the memory stage, and it's followed by an instruction that needs this result at the execution stage. So let's look into this example. I hope I have a, yeah, here, for example. So let's say I have a load instruction that is going to write register 3, but this is only going to happen at the end of the memory stage. And it's directly followed by an instruction that reads R3. Can I forward right now? Well, if you draw the pipeline, see if we have the pipeline somewhere. Okay, no. If I draw the pipeline, I would say for the load, it's fetch, decode, execute, memory, write back, and that's the load. For the add, I fetch, decode. When I come to execute, no, I should start one cycle. Okay, so this is fetch. This does not exist. Decode. If I try to execute here, well, I don't have the result. I cannot also forward it. It's not ready here to be able to forward it. It's only ready here. So it's ready in the future, right? So forwarding doesn't work. And your only possible solution is to simply stall for one cycle, insert a bubble, and then do the execution once it's done, right? So this is one very unique example that forwarding or bypassing does not really help you, and it does not completely hide the stalling time. In all previous examples, we didn't need to stall at all. But now we need at least to store one cycle to get it. This is called a load use dependency. A load use dependency is one of the known problems in architectures that, in fact, people up to the moment still really try to find solutions to really hide completely, right? People even don't want to be that extra cycle, right? Okay. So it's called a load use dependency, and you have to wait for it. One possibility that, in fact, there is a very recent paper from Intel last year that they say, okay, something that's similar to what you do in Lab 2 for branches right now. Say, okay, I cannot really execute the load right now. In architecture, there is nothing you cannot execute, just speculate, right? That's a very common technique that people use all the time. If I cannot really execute, just speculate it. So if you predict it, you don't wait until the value is getting back, but rather try to predict what the value might be based on some history, and then you use that value. If you turn out to be wrong, then you have to reflash and reiterate and add some extra delay. But if your speculation is 90% of the time correct, then you save 90% of that stall cycle, right? So that's one possibility that they will try to do. Another possibility that they will try to fetch the data from the memory earlier, right? So instead of doing it at the memory stage, they do it directly after they discover it's a load operation. And they go to the memory early to bring it, right? Okay. There is a lot of interesting stuff happening because of this load use dependency. And I always find it a very interesting problem to teach you on an exam, right? Like think of a solution. If I modify the pipeline in that way to solve the load use, what other implications I might have, right? Because it's a nice problem to think about. Okay. Okay, so yeah, and this is basically adding some of the stall logic. So right now, it's not a bypassing logic, it's a stall logic. When do I need to stall? If my previous instruction is a load, and I have one of the sources dependent on the destination. And there is one very important condition here, that my instruction that follows the load is not a store. Again, why that's the case? Why I need to exclude the store from being the destination instruction? It does not need that result here at the execution stage. It needs it at the memory stage. So we did in fact have an example where there was a load followed by a store that had a dependency, and we didn't need to store because it's a memory to memory forwarding, right? If this was a store, then in fact the pass that's going to happen is from this one to this one, right? Because you need a value that is output from the memory stage, and you feed it back to the memory stage. This is why you exclude the store. In the case of a store, you don't need to wait, right? Make sense? This silence is a little bit scary, whether you get it and it's all fine, or went to a level that, well, you know what, I don't know what you're talking about. Feel free to ask questions, right? We're not in a hurry, so just feel free to ask questions. No? Okay, so you have the slides. Hopefully, you take some time to consume them, and then if you got questions, yeah, just ask in next lectures or drop me an email, and we can open up. This is basically the store bubble I inserted, and that's the store. Good. Yeah, because load use stalling is a scenario that I need to insert bubbles in the pipeline. It impacts more the performance, because bypassing has hidden most of the performance penalties, except up until now for this use case, right? And we didn't discuss branches yet. So assume I want to go back from my performance lecture and try to recalculate things based on the fact that I need to take this into account right now. And I believe this also aligns with the question that was asked earlier: is why do I need to care about frequency of the stores and the type of the stores, right? So assume I have a program that has 20% branches, 20% loads, 10% stores, and 50% just other instructions. And I was given one extra piece of information. So I'm adding up to the performance problems we covered earlier, that 50% of the loads are followed by a dependent arithmetic instruction, right? And I'm giving you that this requires one cycle store, insertion of one knob in the middle, right? So the penalty here, this line is defining the stall penalty, right? And this line is defining the stall frequency. Good. To calculate the CPI, well, ideally it's 1. It's a 5-stage pipeline, so it's 1. And then there's some extra delay that simply I need to store for one cycle. This happens 50% of the time, but this happens 50% of the time of the loads, right? So because I'm saying 50% of the loads. How many loads do I have total? 20%. This happens 0.2 multiplied by 0.5 times. That's the frequency. And in that case, the new CPI would be 1.1. Good. So you suffer a 10% performance penalty because of the load use case. In case that your program has only 20% loads, and half of these loads causes you this extra power. Okay, so how can we reduce some of the frequency thing? There are multiple techniques. Here I'm inserting this load dependency, but one possibility is a compiler can in fact try to schedule instructions, and this is also a very common technique. If the compiler tries to stall an instruction, if the compiler detects dependency, it can hide it. It can reorder instructions for you, right? So in that case, I'm having 4 instructions. The subsequent instruction for the load is using its register, but the sub one does not use it. A very simple solution, if you look into the code snippet, is, well, bring this one here. If you bring this one here, you don't alter the program final output, right? Because there is no dependency. But then once you do this, what did I gain? Well, if you draw the pipeline, I never need to store right now. Why? Because the ADI, when it needs the R4, at the execution stage here, the load would have already done the memory stage, right? So if you're able to insert one instruction in the middle between the load and its dependent instruction, then you hide the store. But this is entailing instruction pipeline reordering, right? It does not happen for an in-order processor. So you either leave it for the compiler to do it, or you have an out-of-order pipeline that does it in the hardware. And this is also another reason why people have out-of-order cores, as we would have in the out-of-order session. Good. So I see that you are moving. So let's stop here and continue next time. Thank you.